the concepts of linear combination and linear dependence that we talk about in this lecture are rather abstract, but they play an important and subtle roles in many areas of mathematics. Generally, okay, let me just say this, generally, we prefer things that are linearly independent. We prefer linearly independent. We prefer things that are linearly independent. We prefer linearly independent whatsoever. Like in the last example, in my co-product example. If I make a new product that is just a linear combination of all products, then maybe it would not sell so well. If my new product is just half a Coke and half a Coke Zero, they are linearly dependent. So maybe it's not that interesting. It's really nothing new to the consumers. But if I make a new line of product which is just a mix of all things, then maybe this is more interesting because they are linearly independent. So generally, we like products that are linearly independent. So maybe I like linearly independent products. Now let's also talk about this next example here. If, for example, I like to solve the differential equation, the second derivative of f is 0, then, well, I can say, for example, my function f could be just 1 then, because the second derivative of 1 is going to be 0, so this definitely is a solution to this guy. Or I can also say x. And that's because the second derivative of x is going to equal to 0. Or someone could come along and say, well, my function could also be 3, because why not? The second derivative of 3 is 0. Or I can also say 5x. Well, the second derivative of 5x is going to be 0. And how about, let's say, 2x plus 7? Again, the second derivative of this guy is going to be 0, and I could just keep writing more. I can have, like, let's say, 9x minus 12, or I can have like 1000x. 1000x plus, let me see, 172, something like that. So the second derivative of all these guys are gonna equal to 0. But if you examine them closely, you'll see that the only two original answers are all we need, because all these guys, they are basically just linear combinations of the two. All the guys that we have down here are just linear combinations of 1 and x. Linear combination of 1 and x. Like, for example, this last guy here, 1000x plus 172, is just 1000 times this guy x plus 172 times this guy 1. So then, if I want to write out the solution to this guy, it is just going to be, let's see, it is just going to be a times 1 plus b times x. And using the terminology from this lecture, I can say that this guy is gonna be just the elements from the span of 1 and x. Because the span of 1 and x are things that could be written as something times a plus something times x. So it's just something times 1 plus something times x. And that's kind of what we have here. So 1 and x, these two linearly independent solutions are all we need. So generally, we prefer linearly independent solutions. We would also generally prefer linearly independent data. For example, if we take a look at my next example here, intuitively, well, if we have more data, then that should be better, right? We like big data. So how come we can't just make copies of existing data just to make new one? Well, obviously manipulating the data is not good, but if you manipulate the data like that, your big picture is not going to be linearly independent. For example, let's say I want to find out what is the average weight of, let's say, a whale. So I want to find out what is the average weight of a whale. So what can I do? I can just go out and find some whale and see how they weight, how much it weighs. So maybe I find one whale and it weighs maybe x1. And maybe I'll just go out and find out some more. Maybe I'll hunt the second whale and it weighs x2. So my second whale weighs x2. And maybe I'll just find some more. Maybe I find the third one and it just weighs x3 per se. But now I'm getting tired, so maybe, well, if I want to find just the average weight of the whale, maybe I can just make up a new data. So I'm gonna find, let's say, a hypothetical whale. Okay. And let's just say this guy, the weight is going to be I'm just gonna compute the average of x1 and x2. Well, like if my first whale weight, let's say like 600 kilograms, and this guy is 800 kilograms, then obviously there should exist like a whale out there that weighs 700 kilograms. So if I make up this new data, my average should also be believable. And I can also do the same thing with x2 and x3, because why not? And I can also do the same thing with x3 and x1. So let me just keep pasting. So here I just keep copying my new data. So this guy is going to be x2 plus x3, and this guy is x3 plus x1. So x2 plus x3, this one is x3 plus x1. So I make up these three new data. But as it turns out, my average for this whole 6 data is not going to be any different from the average from the 3 data that I have. So when we make out new data like this, these are just linear combinations of old data. Linear combinations of, let's see, x1, x2, and x3. And creating data this way would not bring anything new to the table, just like the way if we make new solution this way, if we just add 3, 5x to x plus 7, something like this, it's not gonna add anything new to the table because it's just a redundant answer from my original 2 answer 1 and x. And same thing here, if I keep adding new data like this, it's not gonna matter because it's just a combination of the data that already existed. Now for the last one, multicollinearity. Well, it is a term in statistics that refers to when my independent variable are not exactly independent. For example, if I like to find if the income of a person has anything to do with, let's see, if the income of a person has anything to do with their education, or maybe their age, or let me say gender, or maybe their age, or maybe let's see, their birth year, their year of birth, okay. So my model would look something like this, A1x1, A2x2, A3x3, A4x4, and then constant A5, so this should be A4. But now this model has a problem because the age and the year of birth have to do with each other. If I knew the year of birth, I can just tell their age. And if I know their age, I can kind of tell their year of birth. So my x3 and x4 here, these two things are correlated. And this is not good when I try to fit a model like this. So generally, we would prefer our variable x here to be linearly independent or generally independent of each other. So in a nutshell, this is what I mean when I said that we generally prefer things that are linearly independent.